So power is the one which is used in order to exert certain energy, that is the force applied on an object. On the contrary, you can say that there is loss of kinetic energy, but it is transformed to thermal energy or sound energy or any other forms of energy. Elastic collisions, there are two things which are conserved, that is kinetic energy as well as the linear momentum. Hello everyone, I'm Vrinda, Faculty of Physics, welcoming you all to the session 5 of Chapter 6, that is Work, Energy and Power. Today in our class, let us do regarding the power. So here we have got power. What is meant by power? So power is the one which is used in order to exert certain energy, that is the force applied on an object. So what is that power? The rate at which the work is done. Or you can even say the rate at which the energy is transferred. You're transferring some certain energy to the other so that there is a work which is done. So what is that power? Power is nothing but rate at which the work is done. So that is all about power. So now we have power is equal to the rate at which the work is done. So here, the work done is given as F into dr by, take this dt towards the other side. So it is force. Work is nothing but force into displacement, which is given by dr by dt, and that dt is nothing but this term is taken over there. So we have got F into dr by dt, it's nothing but change in position with respect to time is considered as your velocity. So we have P is equal to F into V, that is force into velocity. So applying force to an object and it moves under certain velocity, then you can say that the work is done on an object, and that is nothing but the power. So what is that power? Power is the rate at which the work is done. So what is the SI unit? SI unit of power is given by work, which is given in joules, joules per second. So it is joules per second, that is the SI unit of power. So now we will have to check the dimensions, and dimension of power is given as F into V, right? So what is the dimension of force? Let us come from the initial state, that is force into velocity. Force we have got mLT minus 2, because mass into acceleration, you have to get the dimension for force by having mass into acceleration. Mass is m, acceleration again it changes to velocity with respect to time. Again we have got dimension for time but not for velocity, and again the velocity is broken down into simpler one, that is position divided by time. We have got mLT minus 2. Now velocity, the velocity formula is position, the change in position with respect to time. So change in position divided by t. So it is length by time taken. So again I can write it as LT inverse. So on the whole you have got L into L, it is L square, T minus into minus minus, but adding, that is T minus 3. So this is the dimension of power. L square T minus 3 is the dimension of the power. So you got to know power's definition and its formula, SI unit as well as dimensions. So suppose if you consider 1 horsepower. So 1 horsepower has got how many watts? So here this SI unit of power is joule per second, and even you can call it as watt, or else it is watt. Okay, so 1 horsepower is how many watts? We have to give the number value. So always it is 1 horsepower is 746 watt. So this is the value of 1 horsepower. So this is all about the power, and the SI unit can be either joules per second or else it can even be watt. And next we are going to the collisions. So now let us take collision. It is nothing but interaction between either two particles or more than two particles which exerts force on each other. So when there is collision between two particles or more than two particles, there is a force which is exerted, because of which it rebounds back. Either it rebounds back or else slight rebounding is there. Either its velocity initially as well as final will be one and the same, or else it decreases because of the deformation which is taking place. So there are two types of collision. One is said to be elastic collision, another one is said to be inelastic collision. Elastic collision, just remember, you people know the common term as elasticity. It's a elastic, how much you pull, so much it gets compressed, right? So here it is elastic, inelastic. So here you have got the example for elastic collision, and this is an example for inelastic collision. That is, whenever you pitch a ball, here a person is pitching a ball. Whenever you pitch a ball, it hits the ground and it rebounds back with the same energy, So here you can say the kinetic energy is not lost, and as well as something is getting conserved over there, because initial states, whatever the condition were there, the final also the same conditions are maintained. So there is conservation. So here there is kinetic energy as well as linear momentum, both are conserved in elastic collision because it is rebounding backwards. Again, in elastic collisions, there is a collision wherein the deformation is given a much importance over there, because the deformation is taking place. So when the deformation is taking place, there is kinetic energy which is lost. Lost in the sense it's not completely destroyed, because according to conservation of energy, energy can neither be created nor it can be destroyed, but can be transformed from one form to the other form. When that is the case, it is transformed to some other energy. Okay, either it is thermal energy or sound energy, any other forms of energy. So first of all, whatever the kinetic energy is over here, it is lost. There is a deletion of kinetic energy, but it is getting transformed to some other form of energy, but the momentum is said to be conserved. Okay, so this is an example for inelastic collision. So now let us see the difference between elastic as well as inelastic collision. As I discussed here, just remember, that is, just keep in your mind the image whatever we had seen here. That is, this is an example for elastic, this is an example for inelastic. Keeping that in your mind, let us give the difference. That is, there is no loss of kinetic energy in the system. So when there is no loss here, on the contrary, you can say that there is loss of kinetic energy, but it is transformed to thermal energy or sound energy or any other forms of energy. So there you get your 1 mark. Okay, next it is kinetic energy and linear momentum, both are conserved. It is not lost. Kinetic energy is not lost. Linear momentum is always conserved. So when there are two things, both are conserved. Here the kinetic energy is lost. So you can just give the statement as momentum, that is linear momentum, is said to be conserved and not the kinetic energy. While coming to the third point, the total impulse of the first object is equal and opposite to the second object. Okay, and when it comes to inelastic collision, here the deformation is the one which is having an important role. So here the impact and deformation during collision leads to the generation of heat or sound energy, because of which there is no equal and opposite impulse. Okay, so there is a deletion. That means the energy is lost to some other thing. So because of which it is not having the same conditions as that when it had during the initial collisions. These things are about elastic and inelastic collisions difference. Now let us consider any object which is colloiding. Okay, so let us consider two dimensions, that is one dimension collision as well as two dimension collision. So now let us go to collision in one dimension. So collision in one dimension is also called as head-on collision. So when can you say this head-on collision? That is when the initial and final velocities, when the initial and final velocities of the particle is along a straight line, we call it as head-on collision. Now, we will have to consider two particles, particle A and B. So, consider two particles A and B. So, suppose you have got two particles over here, A and B. It is having certain mass m1 and m2, which is moving with initial velocity u1 and u2. So this event is taking place before collision. Okay. Consider two particles, that is A and B, which is having their masses m1 and m2. By looking at the diagram itself, you will have to explain how exactly we can give a statement for the following derivation. There is nothing difficult in giving the statement to this. So the thing is, first of all, you just imagine this drawing. Okay, so there are two circles over here, which is considered to be a particle. Okay, so which is rolling and which is hitting, and the initial velocity is u1 and u2. Okay, so consider two particles, particle A and particle B, which is having mass m1 and m2. So consider two particles AB with masses m1 and m2. So particle name as well as its mass is clear. We are left out with initial velocity. So mass m1 and m2 moving with initial velocity u1 and u2. So this velocity becomes velocities. Okay, because two velocities are there. So initial velocity is u1 and u2, and velocities after collision. So we have to check velocities after collision. That is nothing but if this condition is before collision, okay, this is before collision. Now we have during collision. It is A and B with mass m1 and m2. This is the time where it collides. Okay. Now, after collision, so after collision, it is like A and B. So this A is having final velocity of v1 and velocity of B is v2. So before the collision, here we have got this velocity will be faster than this. Only then this can collide with the second object, right? So u1 is greater than u2 in this case, and collision takes place, and then after collision that is the final velocity of the second particle V2 moves faster. So velocity of V2 will be greater than V1. I hope you're clear with the statement how it is and the diagram, that is before collision, during collision as well as after collision, what is the condition, correct? By looking at this, we are talking about the elastic collision. Here we are talking about the elastic collision in one dimension. Okay, so as you all know, when it is elastic collisions, there are two things which are conserved, that is kinetic energy as well as the linear momentum. So now we told that elastic collisions both are said to be conserved. What are those both? Linear momentum and kinetic energy. So here, according to conservation of linear momentum, we have m1u1 plus m2u2, which is equal to m1v1 plus m2v2. Okay, so we can get it as m1u1 minus v1, because you're taking this m1 this side. Again it is m2 into v2 minus u2. So this is the condition. So this can be said as equation 1 and this can be considered as your equation 2. Now since the kinetic energy is also conserved, we can consider it as kinetic energy. It is half m1u1 square half m2u2 square, which is equal to half m1v1 square plus half m2u2 square. Okay, now we can cancel the halves because it can be taken it as common, v2 square. So m1u1 square plus m2u2 square remains, m1v1 square plus m2v2 square remains. So we can do it as m1 into u1 square minus v1 square, which is equal to m2, we can leave it as v2 square minus u2 square. So this is of the form a square minus b square, which is having a formula of a square, a plus b into a minus b, a plus b into a minus b. So here we have got m1 and it will be u1 plus v1 and u2, u1 minus v1, which is equal to the same thing, m2 into v2 plus u2 and v2 minus u2. Okay, now dividing equation 3, so let us consider this to be equation 3. Dividing this equation 3 by equation 2, we have got m1 gets cancelled with m1, u1 minus v1 gets cancelled here, and m2 gets cancelled with m2 as well as v2 minus u2. This gets cancelled with this. So what are we left with? u1 plus v1, v2 plus u2. u1 plus v1 is equal to v2 plus u2. So now u1 minus u2 is equal to v2 minus v1. So this can be considered as, this is relative velocities of A with respect to B in terms of initial condition. This is also the same thing, relative velocities of A with respect to B in final condition. Here it is in initial condition. Okay, so this is how it is, that is relative velocity of A with respect to B in initial as well as in the final condition. Now, we will have to check up that it is, so it's like relative velocity of approach is equal to relative velocities of separation. Relative velocities of approach is equal to the relative velocity of separation. Now, let us calculate what are the final velocities, that is V1 and V2. In order to calculate the final velocities, you will have to keep something in your mind, and that something is nothing but this equation star. You can even name it as, if you're not comfortable with equation star, let me name it as equation 4, because 3 is already over, so it's 4. So we have got what? The equation 4, which gives you the relative velocity of approach as well as the relative velocity of separation. So now we will have to check up, that is, what is V1 as well as V2. So now we can write this as, you can just write it as V2 is equal to U1 minus U2 plus V1. U1 minus U2 plus V1. So we know the value of V2. Substitute for V2 in the equation of momentum, that is conservation of linear momentum. We have M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. Substitute for V2. What do we have? U1 minus U2 plus V1. So, M1 U1 plus M2 U2, which is equal to M1 V1 plus M2. V2 is nothing but U1 minus U2 plus V1. U1 minus U2 plus V1. So, how can you write this as? M1 U1 plus M2 U2 is equal to M1 V1 plus M2 U1 plus into minus minus M2 U2 plus into plus is plus M2 V1. Here we are equating for the velocity of the particle, first particle after collision. So retain your V1 terms there. So you have got M1 U1 plus M2 U2. Retain this V1 because we have to calculate V1. So retain those terms there and get these, that is M2 U1 and M2 U2 this side. So minus M2 U1 plus M2 U2 is equal to M1 plus M2, taking V1 as common out. Okay. So now we have got M2 U2, M2 U2. That now we have got M1 U1 minus M2 U1 plus 1 and 2. So 2 M2 U2 is equal to V1. Get this M1 plus M2 to the other side. Now split the terms. That is, you have got U1. So you can write it as M1 minus M2 divided by M1 plus M2. So this can be treated under U1 plus 2 M2 U2 divided by the same thing, you're splitting M1 plus M2, okay, which is equal to V1. So this is the one which gives you the value of velocity after collision of the first particle, that is particle A. Now let us consider the velocity, the final velocity of the particle B. So the same way how we have gone through with this, similarly you can just go with the velocity of the second particle, wherein the velocity of the second particle will be, in the place of this 1 you will have 2, M2 minus M1 divided by M1 plus M2 and U1 as it is plus 2 M1 U2 divided by M1 plus M2 is equal to V2. That is how you get for the second velocity. So this is all about the collision in one dimension. So in today's class, we had studied regarding the power. So definition of power, its SI unit, the dimensions, as well as we studied regarding the collisions. So collisions, there are types of collisions, that is two types of collisions, elastic collisions and inelastic collisions. Under that elastic collision, we had studied the collision of the particles in one dimension. So here we are done with the today's session, that is from the chapter Work, Energy and Power. Thank you. Have a good day.